Hello once again, class, and welcome to another mock lecture. The audio for this one might sound a little bit different because I'm not recording in my usual space. Could be a little bit echoey. I guess I'll find out when I start editing this thing. But today what we're going to be tackling is L'Hopital's rule. So to set this up, I just want to start where we began for this whole differential calc series that I've been doing. We started with limits. We needed to know what is a limit, how do we find limits so that we can define these things called derivatives. And that's basically what this whole course is about. We use derivatives, we learned implicit differentiation, we used derivatives to do curve analysis. We did two major applications from both of those things. Curve analysis gave us optimization and implicit differentiation gave us related rates. But today what we're going to do is we're actually going to apply derivatives to limits as well. So limits helped us define derivatives, but derivatives can help us find limits that we haven't particularly looked at yet because we haven't really known how to take them. And in that sense, we're coming kind of full circle here. And that's what I really like about this calc series, is that we kind of end where we began, which is pretty cool. Now, granted, differential calculus is just a small portion of the mathematics map in general, but today's focus is going to be on finding limits of expressions that yield something that we don't actually know how to calculate. To be fair, though, we've actually seen some examples of this before. For example, the limit as x approaches 1 of x squared minus x divided by x squared minus 1. If you try to use direct substitution, that gives you 0 over 0. The way we handled it back then is we said, well, wait a minute, that doesn't make any sense. Let's see if we can algebraically do something to make it so that we can now use direct substitution. In this example, factoring the numerator and the denominator helped us do that. But what if we run into something like this, which also produces 0 over 0, but there's no algebraic trickery that we could do to help us solve this, right? Similar, and this is actually the same function, but now at infinity instead of at 1. Now we get something that's infinity over infinity. How do we calculate these things? What are these things? Like, for example, is 0 over 0, 0? Is it 1? Is it undefined? Because it has 0 in the denominator. And if it's undefined, then is this limit something that doesn't exist? Right? These are the questions that we're going to tackle for today. 0 over 0 and infinity over infinity, by the way, are examples of limits that yield indeterminate forms. Right? Or I guess I should say these things are examples of limits that yield indeterminate forms. These things are indeterminate forms, which are expressions that we obtain from limits that we just don't know what they are. We don't know how to calculate those things. There's 7 of them in total, 7 main forms, I should say. There's type 0 over 0 and type infinity over infinity. But then all these other ones are similar question marks, like what's 0 times infinity? What's infinity minus infinity? What's 1 to the infinity? What's infinity to the 0? And what's 0 to the 0? We don't know. I say main types because you can just have negative infinity instead of infinity, except for this one, right? This one is explicitly you're taking away infinity from infinity. But all these other ones that involve infinity, you could have negative infinity as well. And they'd still be a question mark, right? They'd still be something we don't know how to solve, which makes them indeterminate. Well, today, we are going to learn a method to deal with these two types explicitly. The first two types, 0 over 0 and infinity over infinity, indeterminacies, are going to be solvable based on what we do for today. And we can use that method that we're going to learn to manipulate the expression that we're trying to take the limit of and also apply it to these other 5 main types of indeterminate forms as well. So essentially, today is about how do we figure out what these things are. And the method that we're going to use to do this stuff is something called L'Hopital's rule. Now, L'Hopital's rule says if you suppose that f and g are some differentiable functions, meaning that they're also continuous, and the derivative of g of x is not equal to 0 near a, which is the thing we're going to be taking the limit towards. But again, because it's a limit, it's actually okay if g prime of a is 0, right? Limits only care about what we're approaching and not exactly what's happening there. And then we're also going to suppose one of two different things. We're either going to suppose that both of the limits at a for f and g are both 0, or that both of the limits at a for f and g are both infinity. Well, what L'Hopital's rule says is that it gives us an equivalency statement for the limit as x approaches a of the function f divided by the function g. And what we're allowed to say for something like that is that that's actually equal to the limit as x approaches a of the derivative of f divided by the derivative of g. Because we're set up at like this, and either 1 or 2 is true, then we're looking at type 0 over 0 or infinity over infinity indeterminacies. It's one of those two things. And if you have a situation like that, you're going to have to verify that these are true to actually apply L'Hopital's rule on that particular limit. But then you can just differentiate the numerator, differentiate the denominator, and look at the limit of that thing. And it would be exactly the same. And by the way, even though it says x approaches a, which kind of supposes that a is a number, it can be a number from the left, it can be a number from the right, or it could be positive or negative infinity. L'Hopital's rule is very broad in that regard. But essentially, if you have the derivative of some ratio that is producing an indeterminate form of type 0 over 0 or type infinity over infinity, then you can actually take the derivative of the numerator and the denominator independently of one another and look at the limit as x approaches a for that thing, which is oftentimes easier to do. With that out of the way, let's look at some examples. All right, example number 1. We're going to find the limit as x approaches 1 of the natural log of x divided by x minus 1, right? This is the first thing that we looked at here. Well, first we have to verify that we do have an indeterminate form. Well, the limit as x approaches 1 of the natural log of x is 0 by direct substitution, and the limit as x approaches 1 of x minus 1 is also 0 by direct substitution. So, okay, let's just use L'Hopital's rule here and say that the limit as x approaches 1 of the natural log of x over x minus 1 is equal to the limit as x approaches 1 of the derivative of the top and the derivative of the bottom. Both of these derivatives are pretty simple to calculate. The derivative of the natural log of x is just 1 over x, and then the derivative of x minus 1 is just 1. So we don't even need this. We just get the limit as x approaches 1 of 1 over x, and I can use direct substitution there, so the limit's 1. Simple as that. Example number 2. Let's say we're looking at now the limit as x approaches infinity of x squared plus x divided by e to the x cubed. Well, I don't know what this is looking at it now, so let's look at the limit of the top and the bottom individually and see if we've got indeterminate form stuff going on. Turns out we do, right? It's not hard to check either. As x approaches infinity of x squared plus x, that's infinity. That's just something it's a polynomial that's going to infinity. And then the limit as x approaches infinity of an exponential function raised to a polynomial is also infinity. So this is an infinity over infinity indeterminacy that we're looking at here. So by the L'Hopital's rule, we can set this thing equal to the limit as x approaches infinity of the derivative of the top and the derivative of the bottom. The derivative of x squared plus x is 2x plus 1. And then the derivative of e to the x cubed is 3x squared e to the x cubed by the chain rule. But you'll notice that this didn't really help. We're kind of still in the same situation, right? The derivative of the top is still infinity, and the derivative of the bottom is even more infinity, which is a weird statement to say. But since we still have an indeterminacy of type infinity over infinity, let's just use L'Hopital's again.
Another one.
Here, we get just 2 in the numerator, divided by, and I did have to use the product rule in this thing, but the point is, this thing grows really, really fast. It goes to infinity. So you've got 2 over something that's getting bigger and bigger and bigger. It's blowing up. And 2, in relation to how the denominator is growing, becomes less and less significant. And so this thing is approaching 0. So our limit as x approaches 0 of x squared plus x divided by e to the x cubed is 0 by double L'Hopital's rule in this case. Example 3, let's find the limit as x approaches 0 of 1 plus the sine of x divided by the cosine of x. And I invite you to pause the video at this point and give this one a try. If you're trying to use the L'Hopital's rule, you can't. You don't have an indeterminate form for this thing. The limit as x approaches 0 of 1 plus the sine of x is 1. And the limit as x approaches 0 of the cosine of x is also 1. So you can just do this with direct substitution. So this is always something to look for. Oftentimes what I find is when I teach students the L'Hopital's rule and they see a ratio, they just automatically are like, oh, let me just differentiate. But remember, you have to check to see if an indeterminacy exists. as your solution, right? You need to make sure that the limit of the top and bottom are either both 0 or both infinity so that you can even use L'Hopital's rule. That's the antecedent of the L'Hopital's rule in general. You have to have that these two things have the same limit and they're either both 0 or both infinity. But let's move on to products. And there's really only one indeterminate product. I mean, I guess you could categorize it as just one indeterminate product. Anytime you have 0 times a type of infinity, that's an indeterminate product. How do we solve these things? Well, if you suppose that the limit as x approaches a of f of x is 0 and g of x is infinity, what would the limit as x approaches a of f of x times g of x actually be? Well, one thing that you can do with products is that you can actually write them as quotients. You just have to divide by the reciprocal of one of these things. And so that gives us two different ways to come up with a quotient out of a product. You can either write f of x divided by the reciprocal of g of x, which is 1 over g of x, or you can write g of x divided by the reciprocal of f of x. Right? Both of these things algebraically get us back to f of x times g of x if you were to simplify either one of these things, because to be fair, they look a little ridiculous. But the point is, this is totally legitimate. Like this is within the realm of what we can do in mathematics. We can divide by a reciprocal. That's the same as multiplying by something. So that's the strategy that we're going to take here. In this example, since I said that f of x's limit at a was 0, then this is type 0 over 0 indeterminacy, this one here. Since we established that g of x had a limit as x approaches a of g of x being infinity, then this is an infinity divided by 1 divided by 0, right? So that thing is getting really, really big. So you have an infinity over infinity type indeterminacy. So that's the general strategy. Once you can get that, then you just use L'Hopital's rule. So let's say that we're looking at the limit as x approaches infinity of x times the sine of 1 over x. Right now, if you were to look at these things individually, right, just apply some limit laws to this, you can look at the limit as x approaches infinity of x and the limit as x approaches infinity of the sine of 1 over x individually. But you find that this one's infinity and this one, doing a little bit of kind of substitution stuff for you. So I changed my limit boundary there, what we're approaching. But I found that that's 0. So this is an infinity times 0 situation. This is an indeterminate form. So what I'm going to do is I'm going to rewrite x times the sine of 1 over x as the sine of 1 over x divided by the reciprocal of x, which is 1 over x. Okay, that's going to give me type 0 over 0. The limit as x approaches infinity of 1 over x is 0 because x is approaching infinity, so the 1 starts to become meaningless, and so that's approaching 0. Now you might wonder, why not write it the other way? Why not put x in the numerator and then just bring the sine down as a cosecant? So you've got x divided by the cosecant of 1 over x. And here's the thing about doing indeterminate product stuff. It actually does matter which one you go with. Sometimes you run into a dead end. If you're going to go this direction, you do need to make sure that the limit of x, right, which is infinity, is fine. You need to make sure that the limit as x approaches infinity of the cosecant of 1 over x also approaches infinity, which it does. There's a vertical asymptote at that point in the graph. But the thing is, if you use L'Hopital's rule on this thing, then you get something that's even more complex than what you started with. And typically when that happens, I go back to the very beginning and I flip the way that I rewrote the problem. In this example, what you end up getting is x squared divided by the cosecant of 1 over x times the cotangent of 1 over x, which is still infinity over infinity. And you could say, well, that's fine. Just use L'Hopital's again. You can do that, but I mean, look at the derivatives you're having to take now. So I would just go with this way, because when you differentiate the numerator, you get negative x to the negative second times the cosine of 1 over x. That's by chain rule. And in the denominator, you just get negative x to the negative second. And so since these are the same, they just cancel. And now this is just a cosine function of 1 over x. We know that the limit as x approaches infinity of 1 over x by itself is approaching 0. So we can just plug in 0 to this function and we get 1. Cosine of 0 is 1. Now we're moving on. Indeterminate differences. What's infinity minus infinity? The only strategy that you have is to hope that you can rewrite the difference as some kind of a quotient. Because remember that you still need to have one of these two types for L'Hopital's rule to be usable. Here we've got the limit as x approaches 0 from the right of the cosecant of x minus the cotangent of x. And the nice thing about trig functions is you can always use some identities to rewrite them. So this is the same as the limit as x approaches 0 from the right of 1 over sine of x minus cosine x over sine of x, for which they already have a common denominator, and here we go. Here's a quotient. Now we just have to hope that this is an indeterminate form. And it is, right? The limit as x approaches 0 from the right of 1 minus cosine x is 0. The limit as x approaches 0 from the right of the sine of x is also equal to 0. So this is type 0 over 0 indeterminacy. And I did that by direct substitution. Okay, so using L'Hopital's on this thing, the derivative of 1 minus the cosine of x is 0 minus negative sine of x. So you get positive sine of x there. And then in the denominator, the derivative of sine of x is simply cosine of x. This is just a tangent function, right? When you take the derivative of the top and the bottom individually. I could have made it tangent, but at this point, it was already in terms of sine and cosine. So I just did my direct substitution here. Plugging in 0 for sine gives us 0. And plugging in 0 for cosine gives us 1. So the answer here is 0, because 0 divided by 1 is 0 by direct substitution. So in this case, infinity minus infinity ended up being 0. That is not always going to be the case, though. But we're not going to look at another example of that, because we need to move on to indeterminate powers. Okay, there's 3 indeterminacies that we haven't talked about yet, and it's all the ones that involve powers. Type 1 to the infinity, type infinity to the 0, type 0 to the 0. What is the limit as x approaches a of a function raised to another function when you end up with something like this? Well, you might have an idea of where we're headed with this, but typically when you have powers and you want to remove powers, you have to use logarithmic tricks. And that's exactly what we're going to do. If we let y be equal to this thing, and then we take the natural log of both sides, which is going to allow us to bring the g of x that was previously here down in front of the logarithm, which is a log property. It's the power rule for logarithms. Then exponentiate both sides with a base of e, then effectively what we've done is we've changed the notation for y. There are no powers anymore. At least, I guess what I should say is, there's no function that's in terms of x that's raised to another function that's in terms of x. The base here is just e, and we can deal with that. So that's the general strategy for how we deal with these types of things when we get indeterminate forms. Here's a very basic example. Let's say that we're trying to find the limit as x approaches 0 from the right of x to the x. What I'm going to do is I'm going to let y, and so by the way, this is type 0 to the 0 because that's just direct substitution stuff. What I'm going to do though is I'm going to let y be equal to x to the x and then take the natural log of both sides. And what that allows me to say is that the natural log of y is equal to x times the natural log of y. But then I'm going to exponentiate both sides with the base of e so that I can just get y by itself again. And that is going to be the same as e to the x natural log x. So I'm going to change the way that my limit looks by plugging e to the x natural log x in for x to the x. Because it's the same thing. They're both equal to y. Y is x to the x here. Y is e to the x natural log x here. There are some domain stuff to consider, but since we're approaching this thing only from the right, I'm going to ignore that for right now. In any case, the way that you would solve this, the way that I would solve it at least, is to change to do some substitution, right? Let's call this u. So this would be the same thing, this entire thing that I put a box around here, now I'm circling it, would be the same as the limit as u approaches something of e to the u, and now I just need to figure out what is the something. Essentially, what is the limit as x approaches 0 from the right of x natural log x? Whatever that is, that's the question mark. That's what I'll put in right here. So let's analyze that. What even is the limit of this thing right here as x approaches 0 from the right? Well, first of all, notice that it's actually an indeterminate form in and of itself. It's 0 times negative infinity. So let's rewrite this as a quotient. The route that I went is I brought x into the denominator as 1 over x, which is going to give me type infinity over infinity. Actually, I think it gives me type negative infinity over infinity. Yeah. But in any case, I can use L'Hopital's on it. The derivative of natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. That looks a little insane, so I went ahead and simplified that to the negative x squared over x, which then simplified to negative x. And at that point, I can just use direct substitution and I get 0. Which means if this thing is approaching 0, then the limit as x approaches 0 from the right of e to that thing would be the same as the limit as that thing approaches 0 of e to the u. And by the way, you'll notice I did put that it approaches 0 from the left, and that's because it's negative, right? You're approaching 0 from the right, but it's negative x, so technically it's approaching from the left. Luckily, we're taking the limit of a continuous function whose domain is all real numbers, so that doesn't really matter, but it is something to note. In any case, I can use direct substitution on this thing. E to the 0 is 1. So in this case, 0 to the 0 ended up being 1. Let's look at
another one.
Let's find the limit as x approaches 0 from the right of some function, 1 plus the sine of 4x, raised to some other function, the cotangent of x. First, we need to assess whether or not this is even an indeterminate form to begin with, but very quickly you find out that it is. The base of this kind of exponential function, 1 plus sine of 4x, as x approaches 0 from the right, you can just use direct substitution on it and you get 1. The power, cotangent of x, again, we're approaching 0 from the right, which is why the limit even exists for cotangent in the first place, because there would be a vertical asymptote there. But the point is, you get infinity. It's cosine x over sine of x as you approach from the right. Cosine as you approach 0 from any direction is approaching 1. And sine of x as you approach 0 from any direction is approaching 0. So this is infinity. So this is a 1 to infinity type indeterminacy. But that's good, right? That means that we can potentially use L'Hopital's on it. So what I did is I said, let's let y be equal to the thing we're taking the limit at 0 from the right is. Took the natural log of both sides. So we have the natural log of y is equal to the cotangent of x, natural log of 1 plus sine 4x, again, bringing down the power because we've got a logarithm. And then I exponentiated both sides. So changing some notation here. We get y is equal to e to the cotangent x natural log 1 plus sine of 4x. So that's what I'm going to replace the limit with. Again, I need to figure out what is this thing doing as x approaches 0 from the right so that I can figure out what e to that thing is doing as that thing is approaching whatever it's approaching. Okay, so I always do this, and so my goal is now I need to figure out, well, what is this approaching as x approaches 0 from the right? So that's what I need to assess. This is also an indeterminate type of infinity times 0. You can see that I did some work for the substitution kind of idea, changing the bounds of the limit for that thing. But in any case, you get infinity times 0 as the indeterminate type for just the power, right, of the thing that we're trying to differentiate, of the thing that we're trying to take the limit of. So what I did is I put cotangent in the bottom as tangent. Trig functions get to move up and down by just changing the function that it is. I mean, tangent is the reciprocal of cotangent. So instead of writing 1 over cotangent of x, I just wrote the tangent of x. But now we have an indeterminate form type, right? We've got, what do we have here? We've got 0 over 0. Is what the indeterminate form for this one is. So I was able to use L'Hopital's rule on it. Taking the derivative of the numerator looks kind of a mess, but it's actually not too bad. It's the cosine of 4x, this is by chain rule, by the way, divided by 1 plus the sine of 4x, and that's all divided by the secant squared of x, because that's what the derivative of tangent is. But then we're basically done with this, that you can actually just use direct substitution now. There's nothing wrong with that. So you just get 4. So if the limit of this power as x approaches 0 from the right is 4, then we can say that this whole thing is equal to the limit as u approaches 4 of e to the u, where we're saying u is this thing. And I can just use direct substitution on that. So we get e to the fourth. So in this case, 1 to the infinity is e to the fourth. Who would have thought? But anyway, that was a ton of examples, and I think that that's enough to kind of get us started with what I want us to work on in class. If you have any questions, please shoot me an email or leave a comment below. Hope you guys learned something. Thanks a ton for watching, and I'll see you in the next one.